This schematic illustrates the respiratory system's mechanical equilibrium, functional residual capacity, or FRC. Here, the lung's inward elastic recoil perfectly balances the chest wall's outward pull. For anesthesiologists, this resting volume is the primary oxygen buffer, preventing rapid desaturation during apnea. We cannot measure FRC using basic displacement spirometry. A traditional water spirometer only measures the volume of air that a patient actively breathes into the physical tubing. The reason for this blind spot lies in the anatomy of FRC itself. Functional residual capacity is composed of the expiratory reserve volume plus the residual volume. Residual volume is the baseline air that remains trapped inside the lungs even after a maximal forced exhalation. Because it holds the delicate alveoli open, it physically cannot be exhaled. Since the residual volume cannot be extracted from the patient and pushed into a machine, simple mechanical measurement fails. We have to calculate the size of this hidden container using indirect biophysics. The limits of those biophysics become apparent when we examine a patient suffering from severe obstructive pulmonary pathology. Notice the severe anatomical distortion of the hyperinflated emphysema X-ray on the right compared to the healthy lungs on the left. To calculate this patient's FRC, a respiratory clinic will typically run two different widely accepted indirect tests. This clinical data table shows the results. First, a helium dilution test returns an FRC of 3.2 liters. Then, body plethysmography is run on the same patient, returning an FRC of 4.8 liters. That leaves a massive discrepancy of 1.6 liters. In a healthy patient, these two tests will yield the exact same FRC value down to the decimal. Here, they are returning dangerously conflicting volumes for the exact same pair of lungs. To understand why the numbers diverge, we must dismantle the physics underlying each test. The first physical principle used to measure a hidden volume of air is the conservation of mass. The logic is simple. If we know the initial concentration of a tracer gas inside a container, and we can extract and measure the total volume of that specific gas, we can reverse engineer the overall size of the container. A patient's resting FRC naturally contains roughly 78% nitrogen, mimicking the composition of room air. To perform a nitrogen washout test, the patient breathes 100% oxygen through a closed mask, washing the nitrogen out of their lungs entirely. This schematic visualizes the math. The FRC multiplied by 0.78 equals the total expired volume times the expired nitrogen concentration. Since the gas analyzers give us three variables, we isolate FRC algebraically to solve for the missing volume. The nitrogen washout test successfully calculates FRC, but it relies entirely on the premise that the gas can physically exit the alveoli to be collected and counted. The helium dilution test uses a closed-circuit alternative to the washout method. Helium is chosen because it is highly insoluble in blood. It will not diffuse across the respiratory membrane and ruin the conservation of mass equation. In this closed circuit, the patient breathes from a spirometer containing a known volume and concentration of helium. As they breathe, helium distributes evenly into the lungs. The equation, initial concentration times initial volume, equals the new concentration times the combined volumes. Both the nitrogen washout and the helium dilution test share a strict biophysical limitation. Gases must freely flow into the alveoli. These techniques do not measure total lung volume, they only measure communicating airways. If a respiratory passage is blocked, these tests simply assume that space does not exist. To bypass the need for gas flow, we have to measure volume via physical compressibility, utilizing Boyle's law. Boyle's law states that at a constant temperature, the pressure of a gas multiplied by its volume is a constant. If a volume shrinks, the pressure of the gas within it rises proportionally. This principle is applied clinically using a body plethysm graph, an airtight chamber containing the patient. At the exact moment of FRC, a shutter suddenly occludes the mouthpiece. The patient makes panting efforts to inspire against the blockage. This physical struggle, contracting the diaphragm and expanding the chest without moving air, is the mechanical trigger needed to map the entire thoracic volume. This tracks double Boyle's law. The patient attempts to inspire, expanding their chest by delta V. This outward expansion compresses the box, raising its pressure, letting us calculate delta V. Simultaneously, the expanding lung drops mouthpiece pressure, allowing us to mathematically isolate FRC. By tracking the exterior displacement of the chest wall against a sealed environment, this mathematical proof extracts the absolute total thoracic gas volume without a single molecule of air needing to leave the lung. We can now return to our COPD patient and the 1.6-liter gap between their helium and plethysmography measurements. The destruction of lung tissue in severe obstructive disease leads to flow-related airway collapse during exhalation. This traps air in enlarged emphysematous bullae. This split-screen diagram shows why gas dilution tests fail. Nitrogen and helium cannot diffuse past collapsed airways, but plethysmography succeeds because trapped gas is still gas. As the thorax expands against the occluded mouthpiece, the trapped air expands, registering on the pressure sensors. The helium test only measured the ventilated FRC, while the plethysgraph measured the total thoracic gas volume. This gives us our definitive clinical equation: total thoracic gas measured by plethysmography minus the ventilated gas measured by gas dilution equals the precise volume of trapped gas. In our COPD patient, that 1.6-liter gap mathematically proves the existence of 1.6 liters of non-communicating trapped air. Failing to recognize this trapped volume drastically underestimates the risk of autopeep and cardiovascular collapse when placing the patient on mechanical ventilation. A discrepancy in respiratory data is not a failure of the equipment. It is a direct biophysical window into the invisible, pathological geometry of the patient's lungs.